It's a quarter past, so that brings us somewhat late into the discussion session, and it's really meant to be a free format. So I'll maybe just kick it off with some questions to Moore and Peter to get them started, and maybe share some additional perspectives beyond what they already covered in their talks, and maybe in particular elaborate on some of the connections that they see with the overall theme of the workshop. But more, Peter and I, we really hope that it will not just be a freeway discussion. And in fact, some of the participants have already agreed to also raise some topics for a discussion. And please don't be shy. So if you have any questions or comments, then please raise your hand, and then we will be able to unmute you so that you can speak up. Now, maybe to get started, and then I could easily fill half an hour with questions, but that again is not the intention. I hope that many of you will join in very soon. But one, I think, sort of aspect that already was touched upon is that the talk of Moore focused more on service time distributions, the talk of Peter on arrival processes. So maybe some questions around that, maybe also thinking of some of the points that Neil Walton touched upon in the talk earlier today. So maybe first starting with Moore. So there's like the distinction, like, is the size of a job known or is it not known? Assuming that the notion is well defined what the size is, or is the age, is it known or is it unknown? Is the distribution of the job size known or unknown? But my guess is that the distinction may not always be so clear cut, that sometimes that you sort of know the distribution and you maybe sort of know what the size of a job is or the age of a job. So if you're in that somewhat fuzzy situation, then do you have any insights, like what is it that we should work on? Should we try to get sort of more accurate information on what the actual size is of every job? Or should we work harder maybe to estimate the distribution of the jobs? And how does that maybe depend on whether we are scheduling or dimensioning? Do you have any thoughts on that question? And I realize that it's somewhat ill-posed and very broad, but maybe any thoughts on that or other things that maybe relate to these sort of like uncertainties in information regarding actual job sizes or distributions?
Okay, let's see. I have lots of thoughts on uncertainty. Where to begin? So first, let me just deal with your specific question, and then I'll give a higher level perspective. But regarding your specific question, sometimes it's not necessary to know exactly what your size is. Whether it's enough to know that you're short versus long. Just 2 classifications is often enough. Or certainly 3 classifications. You don't need to have perfect knowledge. That's for sure. That said, when you're starting to deal with these rank functions, you can end up with real problems when things are a little bit off. Not necessarily the size being off, but the age being off can really mess you up with respect to the rank function. So what I think is more important is to come up with scheduling policies that are more robust against uncertainty. So I would say develop the scheduling policy, like say you have a rank function, that goes up and down. How can you construct a rank function that is robust to what if there is uncertainty in the age? Should you shift the rank function? Should you flatten the tops, the peaks? How do you basically change it so that it becomes more robust in case there's error? So that's the direct answer to your question. I have higher level views on like where we're going, but maybe I'll let other people answer some things first, or.
Yeah, I would maybe proceed with a similar question to Peter, and then we can go back to these sort of higher level questions indeed, which I think would be very interesting. I guess, Peter, in a way you already sort of touched upon that, like maybe what is it that we want to know about sort of arrival processes? I think Neil Walton, I'm not sure if he's still around, made an observation earlier today, and I'm maybe somewhat paraphrasing, that sort of having information on future arrivals could perhaps be even more valuable in certain routing problems, for example, than having precise knowledge of the parameters of the arrival process. So I was wondering if any of these issues also come through in your models, for example? Like, is it that we need more knowledge of actual the realizations of arrival times, or is a better understanding of the parameters or the statistical properties, is that more important, and how does that maybe depend on the timescales that we care about, or the size of the system in terms of basically the number of resources that we are looking at?
I think there's a situation where this distinction that I made between planning problems and operations problems becomes quite important. So, and I think that questions about future information are clearly quite important within the context of a real-time operations decision that one needs to make, or a scheduling decision that one needs to make in real time. The time scales that I was talking about, related to weeks or months, but possibly even years. Of course, any highly granular simulation that you would do of the system probably would want to model the fact that if the protocol that's being used is taking account of future information, to build some model for that within the simulation itself. But I don't, I'm not sure that there would be a direct impact on the type of modeling considerations that I was considering in the planning context per se. But certainly very important in terms of real-time decision making. Okay,
yeah, that makes sense. I noticed that Daryl Peach raised his hand, so let me unmute him, because it's, I guess, extremely late for him, so the earlier he can speak, the better. Daryl, please go ahead.
Hello, how are we doing? Can you hear me? Yes.
Yes.
Hey, Daryl.
Yes. Hi, Peter. I actually had a question for him. I could have jumped in earlier, but this topic is even better to, I think, to raise it. It's concerning this idea of the semi-experiments. I think they could also be used more generally as a kind of informal hypothesis testing. So if we could postulate, so we're looking for, we would like to understand structure and arrivals, particularly if we want to predict in advance, what might happen. If we form a hypothesis of some kind of broad class in which the arrivals may fall, then we can play semi-experiments to test implications of, effectively to see whether the outcomes of experiments we can perform would be consistent with the structure that we've assumed. So it could be a kind of informal hypothesis testing, which could target explicitly attempts to see into the future, which is always handy, but also other aspects. For example, how to link, how to observe features, how to explain, observed features like the covariant structure, and how it depends, how it can be a function of a varying mean.
Yeah, I mean, I agree totally with that. In fact, that was to some extent the intent of the semi-experiments, that the exploratory data analysis that we've been doing. The first times that we did this, and it was just basically a question of looking at the various histograms that were created and just eyeballing whether the histograms looked roughly the same or not. And of course, you can also put that into a more traditional hypothesis testing environment. And in today's talk, we did use Kolmogorov-Smirnov to try to formalize some of that hypothesis testing framing. But I definitely think that the semi-experiment framework is one that is a powerful environment for doing hypothesis tests of the type that you were just describing. So certainly one of the things that, one of the main goals of this kind of work is doing exactly that type of hypothesis testing.
Yeah. Okay.
There's a comment from Harsha, I think relating to what Peter mentioned earlier, that Stidham I think already distinguished in earlier work indeed between design versus control of queuing systems. I'm not sure, Harsha, if that's something you want to further expand on, then please raise your hand and then I can also unmute you if you want to further elaborate on that. If not, then yeah, maybe I'll turn it back to, Amy, I think you raised your hand. Please go ahead.
So I feel like I kind of want to combine the talks, because you focus kind of more on the general service time distributions, and Peter, you kind of focused more on these time variant arrival rates. And it kind of makes me think about, there are policies that don't use arrival rate information, right? CMU doesn't, SRPT doesn't. That doesn't necessarily mean they're always going to perform well, and there are policies that do use arrival rate information. And so I guess what I'm trying to ask is, what can you tell me about policies that are going to be robust to the arrival rate? Are there situations where maybe I really can kind of have the best of both worlds, get the general service times and the time variant arrival rates? What do we know about that?
Or do you want to try your hand at that?
Really don't know what to say. So.
Okay, I'll ask a specific question. So in the sophomore,
yeah, let me just try to put it all in a more general framework. So the issue is like this: you're trying to figure out how long a job is going to take, okay? And normally there's a certain amount of work that's ahead of the job, okay? And that might be the jobs that are smaller than it or something like that. Maybe they have priority, okay? And then we think of those jobs that are smaller than myself, as coming in at some rate, some constant rate, okay? And maybe a busy period is created out of those jobs that are ahead of me, created by those jobs starting a busy period. And basically before I can run, I have to wait for that busy period to finish, okay? That's normally how we think about scheduling. So if we're trying to think about, what is my response time, we think about, the jobs that have priority over me, and then a busy period created by them. The problem that you raise now is, suppose the arrival rate of those other jobs, those jobs that have priority over me, can start changing, and in particular can get very high. Now I might have to wait a very, very long time, okay? I can't bound how long I'll have to wait. I haven't heard of scheduling policies that might start to restrict those jobs or change, but that's what I'm picturing, is that something where, where if there are too many smaller jobs that now have priority over me, I might cut them off after some point. I haven't thought about that, but that's what I'm thinking off the top of my head.
Yeah, I think also that this question of robustness of a particular, let's say, scheduling rule, and it's a great question. One way, again, to potentially answer these types of questions is to do things like simulations and look at the robustness across lots of different potential types of arrival streams. And the types of things that, for example, I discussed this morning would be quite relevant to that, in the sense that in some settings, the fine structure of the arrival stream, for example, are the inter-arrival times gamma distributed or exponentially distributed or uniformly distributed, probably has no impact on certain types of performance characteristics for these systems. So, this framing of how to think about arrival traffic is useful, I think, in terms of understanding what different types of simulations you'd want to do For example, in the call center context, everything argues towards potentially doing simulations that are exercising modeling variability across the correlation structures that one uses when correlation is measured at the level of service time scale, but not worrying about the small stuff, so to speak, namely who cares about whether the interarrival times are exponentially distributed or not. So, at the end of the day, when at least when one thinks about decision making at the planning level type of level, one is certainly going to be doing some robustness checks, and you don't know precisely what sort of offered load you're going to see in the system in 3 months from now. So you're going to, do simulations with various different types of traffic mixes and try to see how robust the system is relative to those different types of traffic mixes.
Okay. Varun, you raised your hand. Please go ahead.
So I think this maybe is still connected. I'm trying to sort of clear up the connection. So in my mind, the world of performance analysis is somehow split into two communities. So there's one, I think, which more maybe largely belongs to where we look at like Poisson arrivals, and we can do sort of very fine-grained analysis of fancy scheduling policies. And then there is the other world where we can model non-stationary arrivals, like maybe Jim Dye's work on healthcare, where we can sort of also model viable length of stays, but we don't sort of have scheduling control so much. It's more capacity planning. And sort of I've wondered if there's a bridge between that, and maybe it's data driven, I don't know, but is sort of the theme that maybe is emerging the following, that we sort of go back to this Poisson based performance analysis where we can maybe come up with tails of distributions, mean response time. What we really want is these metrics in a non-stationary setting, and somehow there's a sort of a principled way of combining simulations with the Poisson based analytical modeling, which tells us how to interpolate or extrapolate the results between there. Is there a data-driven way of doing that? Is that sort of where we are going? I wasn't clear whether Peter sort of suggested that theory where somehow there's a principled way of sort of designing simulation experiments to go from one to the other.
Yeah, so Moore can tell me if I'm wrong here, but my sense is probably much of the modeling that people do with Poisson processes isn't so much because one believes that the model is completely accurate or really accurate at a predictive level. And one's doing it because one is getting qualitative insights into how to build a good control policy, for example. And then we hope at the end of the day that it's pretty robust in terms of model departures from the basic assumptions that we make. So it's an analytical framework that we can use quite effectively to identify particularly promising good policies. Predictive accuracy is not necessarily the sort of main criteria that's being used to drive those types of models. And in fact, maybe I'll just take this opportunity to say, I think that's where a lot of the stochastic modeling community's contributions have been historically. It hasn't been necessarily to building models that we believe in our heart of hearts are going to be accurate models at a predictive level. We're building stylized models that we believe in our heart of hearts will generate policies that will perform well in practice and give us a principled vehicle for identifying those good policies. So, it's so if you look at the many of the things that I think we would view as being major contributions of the field over the last 20, 30 years, they would lie in that vein. As you move into an environment where one is more interested in getting things that are somewhat accurate at a predictive level, then the stakes get higher in terms of trying to build models that are actually good representations of reality. And so, for example, I think in the planning environment, I think it's you can make a good argument that oftentimes having some reasonable level of model veracity is going to be important, because one potentially is going to deploy a system that's intended to meet certain quality of service constraints and so forth in the real world. But I don't think, the types of things that are often used within the scheduling environment, again, Moore can correct me if I'm wrong, but I don't think typically people are necessarily assuming that those models are sort of gold standard representations of reality. They're really being used as stylized representations.
I completely agree.
So the takeaway from the sort of Poisson-based modeling should just be my metrics depend on these features of the input, like variance, covariance, and then some of design simulation experiments where we change these knobs to sort of figure out the predictive or build better predictive models. Is that maybe an accurate summary?
Are you asking Peter?
Both actually. Whoever wants to step in, yeah. Like, so how should we sort of, what should be the takeaway from each of these things? So from Poisson models, so there's one thing which I think came clear, which is just better control policies. And we can only design better control policies in a sort of very nice model. But then is there something else beyond just the design of the policy? So for example, I know that the tail of the response time depends on certain features of the input. Maybe that's another nice analytical summary, and then we can sort of design simulation models where we can tune those parameters in the model, which maybe is more faithful to the application. So sort of what's the bridge between Poisson-based modeling? Is just the policy and that's itself, or something more beyond the policy and the analytical expressions can also be useful when we go to an application and planning problems? And maybe it's a fairly open-ended question, so it's fine if.
Okay, so I totally agree that we have to find some way to take arrival, especially changing arrival rates, into account. And we haven't dealt with that. And I think that was at the heart of Amy's question too. What if the arrival rate changes, or what if the arrival rate of certain types of jobs or certain sizes of jobs suddenly changes? What in the world are we going to do about it? I just don't think we've developed that yet. That doesn't mean that that's the only thing that matters here. So the way that I see the world right now, there's a big crisis in underutilization of data centers. When you look at data centers all over the place, there's a big crisis of underutilization. And how did this happen? Okay, so underutilization, by the way, is a big problem. Okay, it's a big problem because the servers are on, they're available, they're just not being utilized, and so they're using power, and and they're using a lot of power, and that's causing all of our problems in our environment. Okay, so it's a big problem. Okay, but why is this happening? It's happening because we've basically let the users determine what their needs are. In the past, okay, when jobs were very simple, you had an operating system, and the operating system basically scheduled the jobs and gave them whatever it wanted, okay? But now we have a world where the users come in and the users specify, I need so many servers, I need so much CPU, I need so much memory, I need whatever. And we let the users handle all that. The users just tell us. And the users tell us because we've become too afraid to schedule. Like, it's too complicated. So we just say to the users, okay, you let me know, what you need. and then we give them that, okay? But the users are terrible. Like, they're terrible in terms of knowing this stuff. They don't know what they need. I mean, they always overestimate what they need. Also, their jobs vary over time, and sometimes they're very parallelizable, and sometimes they're not at all parallelizable. Sometimes they only need one core. Sometimes they need a lot of cores. You know, they're crazy, okay? So the users are not good at representing what they actually need, especially at instantaneously. They might be able to say, okay, this is the max of what I need, but in terms of what I need minute to minute, you know, just like Peter said, you know, the arrival rates can change, the job sizes themselves can change. Users are bad at this, okay? So users give you an upper bound. And then we, in terms of like in the data centers, you know, people who are managing the data centers, we just allocate what the users asked for, and we end up with servers that are underutilized. The way that I see data-driven scheduling helping is, for example, there's a beautiful paper from Stanford on Quasar. It's by Christos, I never know how to pronounce his last name, Kozirakis or something like that, Kozirakis. So he wrote a paper, I think it's 2014 or something, it's at Stanford. He wrote this paper, and he said, what we really should be doing is a lot more of profiling the jobs when they come in, and then using machine learning to actually match the job to other jobs that are similar, other workloads that are similar, so that we can kind of glean over time, what is the speed of for this job? You know, what is the behavior? It's not just the size, it's also how parallelizable is it? How much interference will there be between this job and other jobs? There's all sorts of other questions, you know, holding costs for this job, like all sorts of stuff. And you want to do some profiling, but you also want to use machine learning to be able to, you know, match it to other jobs so you can know something about it. And once you know more about the jobs, maybe now, and this is the part that the paper doesn't go into, but this is the part we can work on, maybe once you've profiled the job in terms of all these aspects, maybe now you can do better scheduling. But I definitely think the systems community has realized that this underutilization is a problem. It's really only been over like the last decade that people have realized we've got problems, and they're very, very eager to start profiling jobs better and getting more data on them so that they can schedule better. It's just that we as modelers need to come in and help people schedule. You know, that's where our expertise is, so we should help.
There was a question and a comment from Avi Mandelbaum in the Q&A. Avi, do you want to bring this up, or would you like me to read it out on your behalf?
Yeah, I can do that. Can you hear me?
Yes, we can hear you. Yes, please go ahead.
Okay.
Yeah.
So thank you to speakers for great talks. I have a comment about the separation, apparent separation of arrivals from services. Because I think that ultimately the problem, and definitely when staffing is concerned, is to estimate the offered load, and the offered load is in fact a function of both. Now, there are environments where counts are important. For example, in airports, there's a physical constraint on how many can be there, so you need to count how many arrivals take place. But in call centers where the queues are logical, then definitely those physical constraints are less important. And then when you think about staffing call centers, then offered load is what actually goes into the formulas. Now, of course, it's another question of whether you can consider them independently when you look at planning as opposed to instantaneous scheduling, but that's a different issue. So I just want to raise the awareness that both are actually, they live hand in hand under the same roof. The second comment is regarding modeling arrivals. And this is biased by my recent interest in over the last few years. When I became aware that in fact, most arrivals to service operations are appointment driven. And that's something that I totally ignored most of my research career. And this has become even more so during the COVID era, where services that used to be free and open now require that you make appointments in order to just use those services. And am I correct to deduce that these appointment-driven elements are actually lacking from our models of arrivals? And just intuitively, they would probably reduce variability, but how much variability will be reduced by appointments is a good question, because appointments change as well. So when you make an appointment, eventually the appointment time is not necessarily, and often time is different than the appointment that you made at the outset. And so analyzing variability of appointment-driven processes is, I know only of one paper that does that. We have data to support the fact that there's lots of variability there. And I just want to make, again, a point that this is something that our community should be interested in. Thank you.
I think that's very interesting. Oh, do you want to talk first, Peter?
Why don't you go first, Mort?
Okay, I just want to second what Avi's saying. I think that I'm noticing this a lot in data centers, that when they look at the requests, a lot of them are reserved requests. So this is a little different than appointment. So it's not necessarily in the future, but basically I want to hold on to these resources for, like, you know, and I'm telling you that I want to make certain reservations. I want to make these reservations ahead of time, and then I want to hold on to these resources. And a lot of requests are made as reservations. It's not a small percentage. And usually in the scheduling world, we just stop thinking about those. Okay, those are reserved resources, and now we're going to think about the stuff that's coming instantaneously. But yeah, anyway, I think I'm definitely seeing it. Go ahead, Peter.
I mean, you raised some great points, Avi. I think, you know, one setting that you could argue is a little bit has some scheduling characteristics to it would be something like arrivals to an airport. Right? People, you know that there are flights scheduled to leave at particular times, and then the passengers that are arriving for that flight basically at some level are randomly scattered relative to the departure time for that flight. In other words, people will make different, let's say, independent choices for how early they will arrive to the airport in order to catch a flight, let's say at 2:15 p.m. in the afternoon. So if you look at that kind of setting, you know, that would be the, you know, in the realm of what I was discussing during my talk with this independently scattered model. That would be a situation where, you know, short time scales, you know, what you would see looks something like a Poisson process, but probably at the time scale that is relevant, let's say, to the TSA checkpoints. You know, what would a TSA checkpoint look like? Well, it's not going to be many server, that's for sure. And there you have enormous wait times relative to the actual service time required to get through, let's say, the X-ray machine. It was much more like a multi-server or single server heavy traffic system. But in that context also, we know when we look at the limit theory, we know that the limit theory says that the relevant timescale that's important to the performance of the system is diffusion timescale, heavy traffic timescale. That's a much longer timescale than the individual inter-arrival times. And one way of describing that might not be to sort of explicitly model the scheduling component, but just to take the view that the overall arrivals to the system, roughly speaking, are something that's described by a process at a diffusion timescale that has certain correlation structures, and then you try to replicate that. And I think when you look at a physician's or a medical clinic, and you look at the arrival process for a medical clinic, there it's very clear that the scheduling of the patients has a very big impact on the structure of the arrival process. And, I think as a consequence, you'd expect to see that the arrival stream has lower variability than a typical renewal style arrival stream. And, that should be taken explicitly into account. But I think, conceivably, in an airport environment where, again, you have something that feels a little bit like a scheduled environment, namely the departure times of the aircraft. And it could be that the type of framing that I talked about today would still be relevant there.
There was a comment from Neil Walton in the chat. And Neil, if you would like to elaborate a bit further, since I think most of the people who we have here now from the US missed your talk. So if you could maybe elaborate a little bit fine. And then make the point that that you were raising.
I mean, the point I was going to make, which Amy's probably seen now, is that for a lot of the cases where the arrival rates don't seem to matter, the proof, there tends to be a proof, and the proof tends to be like a coupling argument or under adversarial inputs or something like that. And so for that reason, they seem to have this kind of robustness property, whereas, as soon as you dive into a stationary distribution, you tend to require some moments. That doesn't give you any insight into when you can get a coupling proof to work out or something like this, or some sort of adversarial proof to work out. I had a kind of another point though I wanted to ask, which I didn't mention in the talk earlier, but when we organized this workshop earlier in the year on kind of reinforcement learning and queuing networks and things like this, and there was a discussion there sort of so Sid Banerjee, Christina Yu, and Jiaoming Zi published this nice paper of a kind of simulation suite called OR suite, so a kind of OR simulation package, if you see what I mean. I wanted to kind of discuss, maybe it's something we don't do enough is sort of use simulations and things like this in order to gain insights, if you see what I mean, or at least it's something that appears a bit later on in the publication. So maybe if something didn't work or you don't have a theoretical result, but you can still get kind of good insights, say, from a model that has a closed form solution and things like this. To what extent should we be doing that? Maybe more. I think we should be doing it more, but others, might disagree, or maybe just the state of models are changing so much that it's not possible for us to have a sort of standardized set of simulation softwares. I mean, more mentioned like SimGrid, which I've used in the past for kind of HPC stuff and things like this. But we sort of within our community, there don't tend to be sort of standardized simulation packages in order to kind of compare our models and kind of share research.
I would say that's true. My students use simulations all the time, but they always write them from scratch. So they just start from the beginning, and maybe they're but they do use simulations all the time. They're trying to simulate
I believe that.
scheduling policy or a new model. It's just they start from scratch. Maybe we do need more packages.
It's not clear, like in computer science, it seems like there are, there's SimGrid, or with the road traffic stuff, there's like Vissim and AIMSUM, there's like standardized packages for those application areas.
Right.
I tried to look for one for hospitals. I couldn't find one, obviously.
Yeah, so maybe depending on the application area, you might have some kind of simulation some simulation package that people use. Mostly what people use are benchmarks, and that's closer to Peter's area here, which is benchmarks to show us like, what do the arrivals look like? What is the arrival process, which includes arrival times and sizes. The benchmarks are really useful. Like when we studied database benchmarks, that's where we saw that jobs, were alternating between, elastic phases and inelastic phases and stuff like that. And, and then we started looking at actual database queries, and lo and behold, yes, this is exactly the behavior.
Mm-hmm.
But the benchmarks really do help. They're more benchmarks about workloads. It's not a simulator. It's not the same thing.
So I think, in that regard, I think, the community owes Avi a better gratitude for the data sets that he's made available to all of us. And these are, at some level, are benchmarks for doing various types of experiments. And I think having more data sets like that available to the community would be very, very useful, very valuable. It's also the case, that some of the types of things that I was discussing in my talk, for example, creating tools that allow us to fit piecewise linear intensities rather than piecewise constant intensities, tools that allow us to optimize the placement of the boundaries to the intervals that are used in doing piecewise constant or piecewise linear fits to a Poisson process. Those are tools that Zuyu and I are creating and will make available probably on his website to the community. So I think hopefully we can move more in the direction of creating software tools and various data sets and various other things that are available to the community, so we don't have to program everything from scratch.
Harsha Honapa also raised his hand. So Harsha, please go ahead.
Thank you, Sam. And thank you, Moore and Peter, for really interesting talks. So I had a question that sort of builds on all the comments so far. So Amy sort of raised this point that, when you have time varying arrivals, it becomes harder to schedule. And, Peter made the point that the utility of stochastic modeling is in getting qualitative insights. And I was just wondering, what are your thoughts on, using machine learning, for example, to gain greater qualitative insight into like scheduling policies, for instance, and or trying to understand large deviations behavior of various queuing systems that have complex inputs and service behavior. And I'm sort of motivated by some papers that I've been reading recently in material science, where machine learning is used to gain insight into molecular self-assembly, for instance, or just how crystals form and so on. It's such a complicated process. You're better off sort of exploring the design space using machine learning. So what are your thoughts about this?
Well, personally, I think that there will be probably many things within our community and within our discipline that will be impacted by machine learning in the years ahead. And one thing that Moore alluded to is that when a customer presents himself or herself, when a job presents itself, there may be many features of the job, many features of the customer that can be observed. And of course, in scheduling decisions and various other things, what you really want to do is take advantage of the feature set that's available to make predictions about what the actual, let's say, service time of this customer is likely to be. So that would be, an example of a setting where having good machine learning models could be quite useful. And you see this, and I've been involved in a fair amount of work at Stanford in the hospital operations environment. And in that context, one of the biggest issues that the hospital is concerned with is the queuing effects that occur when you have customers or when you have patients recovering from their surgeries. So you have a ICU occupancy, various other things that you need to try to monitor quite closely so that you don't overflow your ICU, your intensive care unit. And those are situations where for sure having a good feature set from which to be able to produce reasonable machine learning predictions about length of stay have a very big impact on the way that you want to schedule those operations in that environment. These are elective operations, obviously. So that's just one instance in which machine learning is already having an impact on something that effectively is a queuing problem.
Thanks.
Let's see, it's sort of on the hour because it's dinner time in Europe. lunchtime on the East Coast, maybe even in the Midwest and Texas. So unless there are any final thoughts, I would like to maybe give the final word to Moore and Peter. Maybe sort of if you have any sort of very broad views that you would still like to share, like is queuing theory entering a new era with all the abundance of data, and what are sort of the new vistas or opportunities or pitfalls? So any sort of maybe broad views to conclude the session, that would be wonderful. And I know it's sort of difficult, but if you have any thoughts, that would be wonderful.
Okay, Peter, do you want to go first?
Okay, I'll go first. I think mathematical model building in general, has at least 3 different uses. One being descriptive, another one being predictive, another one being prescriptive. And I think that the community's focus historically has been largely on the descriptive side, to some extent also on the prescriptive side. We've put a lot of energy into stylized model building. And, there clearly is enormous value to doing that. And many of the things that Moore was talking about are insights that come from analysis of stylized models. And I think that will continue to be an important domain of contribution for the stochastic modeling community for many years to come. I also think that we are entering an era where with the amount of data that's available and the types of data that's available, we're now moving into an environment where predictive modeling, possibly in support of prescriptive modeling, is becoming more and more important. And so paying much more attention to data issues, much more attention to model building. Once you go in that direction, I think that the nature of predictive model building being what it is, the models get sufficiently complicated that you really are thinking about building this on top of a computational engine, not doing closed form analysis. And so thinking about how is it going to be used computationally at the next step? What sort of simulation you're going to build based on this? Is this type of model going to go into a Markov decision process? All of those things begin becoming very important in terms of how you do the model building, how you do the statistical analysis, and so forth. But I do think, more and more of our energy as a discipline is going to go into thinking about the interaction between data and the types of modeling issues and modeling environments that we've been historically interested in.
Okay, thank you. More anything maybe in the area of stochastic scheduling? You mentioned the profiling, so to me that sounds very much like a data-driven view of the world. Anything you would like to say there?
Yeah, so I definitely think this is a fantastic time to be a queuing theorist. So I think there are queues all over the place. I think that the data, all these data-driven approaches are just helping us. They're helping us learn. They're helping us get the information that we need about jobs, about how parallelizable they are, about like their speed up functions that I mentioned, about all sorts of, interactions between jobs. We're getting that data now so that we can do better scheduling. And that's fantastic. I think that we will start moving in other directions as well. I think that today, we already have data available, and in many places we never did before. Like there's traffic, traffic programs going on that indicate, like, to self-driving cars where traffic is appearing, where it's going to appear. There are models that are coming up saying, cars are going to be showing up here, or my son goes to get coffee at Starbucks or something like that, and he knows ahead of time exactly what the queues are going to be like, so there is data available that we never had available to us. People can know before they get to the emergency room what the queues are, what the number of beds, all sorts of information is just available, and more is going to become available as people start, wearing chips, as the books on the bookshelves start having chips inside them. We're going to know all sorts of things that we didn't know. So So the amount of stuff that we can do with this data in terms of being able to predict queue lengths or environments or whether we want to go to one place or another is going to become tremendous. I think from a queuing perspective, it's not just even what Peter said, which is being able to predict and being able to schedule. I think those are both good, but we can even go further. So we can look at work like the work of Haseen and Haviv at incentivizing users. So, and I think that that will be a big direction. You know, can we incentivize users? Can we pay people to, you know, take that road as opposed to this road? We're already doing a little bit of that, but can we pay them to use one data center over another? You know, can we charge less or charge more and incentivize the users to go in different directions? I think that will become a bigger area. I think that in terms of drawbacks, there's all sorts of drawbacks. And the biggest problem is privacy. And I think this is the problem people mention all the time. I mean, even when you start charging people, some people are willing to pay more and some are willing to pay less. You already know like what their financial status is or how important things are to them, that they may not have wanted you to know. We have privacy problems all the time. I know what my husband is looking at on the internet because I start getting ads for it. So I'll start getting ads for sneakers if he's looking for sneakers. I mean, we've got privacy all over the place, right? So yeah, so that's kind of the problem. But in terms of information, so much information is going to be available that people who work on queues or scheduling or capacity provisioning or any of that stuff, it's a great time to be in our field.
Okay, well, thank you very much. And also, well, thank you both, Moore and Peter, again, for the wonderful talks and for the very inspiring perspectives that you shared with us. And also big thanks to everyone in the audience who contributed to the discussion. So clearly, there are many topics that I think would merit further discussion.